This is another version of the activity series, and one of the things I wanted to use it for was to explain to you about acids and why some metals don't react with acids. So if I take lead or tin or nickel, anything that's above hydrogen on the activity series, because remember, these are more active or more reactive, and these are not more reactive. These are less reactive. So if I take a metal that's below hydrogen on the activity series, let's say copper, and I put it into a solution of HCl, and I ask myself, will this reaction occur? Well, copper is below hydrogen on the activity series. Hydrogen's a +1, copper is a 0. This reaction will not occur. So you can take copper metal, throw it into hydrochloric acid, concentrated hydrochloric acid, and this reaction does not occur because copper is below hydrogen on the activity series. Whereas any metal that's above hydrogen on the activity series, that's going to happen. That will, that replacement, single replacement will occur. Okay? So metals which are higher on the activity series are more likely to oxidize. Metals which are lower on the activity series are more likely to be reduced. And we're specifically talking about their cations being reduced. So reduction, oxidation, here's copper and silver nitrate. If you go back to the activity series, you can see copper is above silver on the activity series, so that reaction is going to occur. The copper is going to oxidize, the silver will be reduced, and you will produce silver metal, which are these beautiful crystals that you can see here. Okay? And you're going to get some copper 2+ ion with some nitrate. This is a soluble salt, so these guys are just going to be hanging out as ions. The redox process in compound formation, when you make an ionic compound out of a metal and a non-metal, that is a redox process. That is a transfer of electrons. So let's do this practice problem. Predict the products of the following reactions. If no reaction occurs, write NR or no reaction. We've got aluminum and we've got copper 2 chloride. So the first thing we want to do is we want to look at the activity series. So here's the activity series. We're going to take a look at aluminum and copper is way down here. Well, aluminum is a much more active metal. It's more active, and more active simply means more likely to oxidize to a +3 oxidation state. So that reaction will occur. So here we go. We do our replacement and we balance our reaction. We're going to go ahead and analyze it. Aluminum is an element by itself, so it has a 0 oxidation state. We determine that copper has a +2 oxidation state by looking at the 2 -1s for the chloride. Aluminum always has a +3 oxidation state when it's in a compound, and then copper is an element by itself. It has a 0 oxidation state. So we know that each aluminum atom will lose 3 electrons to become a +3 cation. Each copper 2+ ion is going to gain 2 electrons to become a 0 oxidation state copper atom. So a total of 6 electrons are lost and 6 electrons gained. We use the coefficients to make that determination. 3 times a +2 is 6 electrons that are gained, and then 2 times 3 electrons that are lost. That's 3 electrons. 2 times 3 is 6 electrons lost. That gives us 6 electrons transferred. So since aluminum is being oxidized, that makes it the reducing agent. And since copper 2 plus is being reduced, that makes it the oxidizing agent. Now, on a test, you may see the entire compound represented as being the oxidizing agent. That's just fine. The more specific oxidizing agent is the copper 2 plus in the compound, but since it comes with the chloride ion, it will typically be represented as the copper 2 chloride compound. If we're going to look at this compound, this is chromium 3 nitrate and silver. So let's take a look at the activity series and see if that reaction is going to happen. So let's find chromium. Here it is. This is chromium. It's sitting right here, and silver is down here. Now, the specific reaction we were looking at is chromium 3 nitrate. Chromium has a +3 charge. I'll show you why in just a second. And we want to know, will this reaction go? Well, silver's the easy one. It has a 0 oxidation state. Nitrate has a -1 charge. There are 3 of them, so this has to be a +3. So if this reaction is going to go, the way it's going to have to go is silver is going to have to be the reducing agent by getting oxidized and reducing chromium. The problem with the reaction is what we actually have here is chromium +3 over here as an ion and silver as a metal, and silver is way down here. It's not very active relative to chromium, and so that reaction is not going to happen. It's a no reaction. Okay, hopefully you're getting a handle on how to make these predictions. So this is a silver metal is below chromium ion, chromium +3 on the activity series. Silver metal cannot lose electrons to chromium +3 and reduce the chromium ion, so we give it a no reaction. This reaction is what we call non-spontaneous. That is, it does not occur on its own. Okay, so this is a no reaction or a non-spontaneous reaction, whereas the reaction above is spontaneous. Assigning oxidation numbers. All right, the oxidation number of an element in its elemental form is 0. Let me show you what that means. The oxidation number of an element in its elemental form is 0. So if you have iron or magnesium or chromium or silver or gold or any other element that's monoatomic and it's by itself, these all have oxidation states that are 0. Now, if it's a diatomic element like chlorine and it's in its gaseous state, it also has an oxidation state of 0. O2 gas is going to have an oxidation state of 0. Same thing for H2 gas, and it'll have an oxidation state of 0, and all the other diatomic elements in their elemental form will have oxidation states of 0. The oxidation number of a monoatomic ion is the same as its charge. So if you see a monoatomic ion like magnesium 2+, that's its oxidation state. Iron 3+, that's its oxidation state, that 3+. Chloride ion with a -1 charge, that's its oxidation state. Oxide anion with a -2 charge, that's its oxidation state. So the oxidation number of a monoatomic ion is the same as its charge. In binary compounds, those with two different elements, the element with the greater electronegativity is assigned a negative oxidation number equal to its charge in simple ionic compounds of the element. So I'll give you an easy one. So here I have FeO. All right. Now, when I'm trying to figure out is what are the oxidation states in this compound. So I'm going to split these up like this. Now, you know metals love to lose electrons. Non-metals love to gain electrons. Electronegativity, this word is a word that describes the propensity for a substance to acquire electrons. Well, non-metals love to gain electrons. That tells us that oxygen is more electronegative than iron, because iron would really like to give up its electrons. Oxygen wants to gain electrons. That means it's more electronegative, so we're going to give it its charge in simple ionic compounds, and that charge is -2, and we write it as a 2- over here. Now, in this compound there is only one oxygen, and so that's going to be a total -2 charge over here, which tells us that we've got a +2 charge here. I probably did this in chapter 2 when we were naming compounds, so that tells you that this is going to be a +2 oxidation state for iron. So this is iron 2 oxide. What if I had iron, got 2 of them over here, and I've got 3 oxygens. So I'm going to do exactly the same thing. I'm going to split these up. Oxygen is the more electronegative, so I'm going to give it its charge in simple ionic compounds, which is -2 or 2-. 3 times a -2 is a total negative charge of -6. All compounds are neutral, and so this has to be a +6. 6 + 6 is equal to 0 charge. That tells me this is a +3. Why? Because I've got 2 irons, so I have to split that +6 up between those 2 irons. That tells me that that's a +3. This is iron 3 oxide. All right? So in binary compounds, those with 2 different elements, the element with the greater electronegativity, that's going to be a nonmetal almost certainly, is assigned a negative oxidation number equal to its charge in simple ionic compounds of the element. All right. The sum of the oxidation numbers equals 0 for an electrically neutral compound, like we had up here, and equals the overall charge for an ionic species. So let's take a look at an ionic species. I'm going to use sulfate, okay? And it's a 2- anion. All right, so I'm just going to split this up. Now, this is not a compound. It's a 2- anion. That tells me that when I get my negative and positive charges, they have to add up to a -2. Oxygen is further to the right on the periodic table, closer to the noble gases. That tells me it's more electronegative, so oxygen by itself has a -2 oxidation state. I have 4 of them. Each one of them has a -2 charge. So 4 times the -2 is -8. Now remember, the overall charge on the sulfate anion is -2, so the number of positive charges on sulfur over here have to add to -8 to equal -2. So that tells me that that's going to be a +6 oxidation state. So that's what we mean when we say the sum of the oxidation numbers equals 0 for an electrically neutral compound and equals the overall charge for an ionic species. Sulfate is ionic. That means it has a charge on it. So here are some examples. I'm going to go ahead and work each of these for you. So this is sodium chloride. Chloride is the more electronegative, has a -1 charge. That means that has to be a +1 charge. You kind of knew that anyway because sodium cation is a group 1 cation. Those are all +1. Chloride is 1 over from argon on the periodic table. That means it just wants 1 electron. It's the more electronegative. It's the one that wants to gain electrons, and those add up to 0. This is H2. It's a diatomic molecule, and it's an element in its elemental form. It has an oxidation state of 0. Let's take a look at CO2 and a couple of its little brothers and sisters. So here's CO2. It's a compound, so all the oxidation states have to add up to 0. Oxygen is closer to the noble gases than carbon is, so it gets its charge. It's the more electronegative. That's a -2 charge. There are 2 of them. 2 times a -2 is -4. So that means that carbon has to be a +4 oxidation state. Well, what if I had carbon monoxide? I have fewer oxygens. Carbon is going to be less oxidized. These two the negatives and the positives still have to add up to 0. So this is going to be -2. There's only 1, so that's a total of -2. That has to be a +2. And so the oxidation state on carbon in this case is going to be +2. Let's do a polyatomic anion that has carbon and oxygen. All right, so this time, this is carbonate. You should know that by now. It's got a -2 charge, so everything has to add up to -2. Oxygen is still more electronegative. That makes it a -2. 3 times a -2 is -6. So since they have to add up to -2, carbon is going to be a +4. And that's the way we do polyatomic anions. Let's take a look at, this is potassium chlorate. So that's going to be KClO3. We split the elements up. Potassium is in group 1. We can go ahead and give it that +1 charge. That's the only charge that the alkali metal cations have. Oxygen is more electronegative than chlorine is. I know chlorine is further to the right, but oxygen is higher on your periodic table, and so it is more electronegative. It gets its charge. There are 3 of them. 3 times a -2 is -6. This is a compound, so it all has to add up to 0. I've got a +1 here, so that gives me a +5 for chlorine. So chlorine has a +5. This is iron. It's an element all by itself, so it has an oxidation state of 0. Let's take a look at calcium sulfate. We split the elements up. Now we get a break on calcium. We don't need it. If this had not been an alkaline earth metal, which we know in ionic compounds has a +2 oxidation state, we could have figured it out because sulfate has a -2, which would make this metal a +2. All right, so here we go. And so oxygen is more electronegative than sulfur. It gets its charge of -2. 4 times the -2 is -8. Everything has to add up to 0. I've got a +2 on the calcium, so that makes this +6. So sulfur is a +6 in this compound. Let's do, I'm going to move it way over here because I'm kind of running out of room. This is aluminum phosphate. Okay, split the elements up. Aluminum, we are lucky. We know that it's a +3. If this were iron instead of aluminum, we would still know it's a +3 because phosphate is a -3 polyatomic anion. So we would know that the metal was +3. But here we go. We want to know what phosphorus is And I'm going to rewrite this because this is kind of sloppy here. Okay, so aluminum, give me a little bit more room. Phosphate. See if I can do a better job with drawing lines. That's slightly better. Here we go. So this is a +3. This is a +3. Oxygen is more electronegative. It gets its charge 4 times a -2, -8. Everything has to add up to 0. So we know that this is +5. Okay, and it's usually the middle element of compounds like this, ionic compounds like this, that you're looking for the oxidation state for. Let's do one more. This is nickel 2 nitrate. And hopefully you know why I'm calling it nickel 2 nitrate. And I'm calling it nickel 2 nitrate because nitrates have a -1 charge, and there's 2 of them. So I know that's going to be nickel 2. But I'm going to go ahead and sort this out. So I know this is +2 because I have 2 -1 nitrates, which gives me a total negative charge on this side of my ionic compound of -2, so that has to be a +2. So I can just drop that down. Oxygen is more electronegative by a little bit than nitrogen, so it's -2. I have 2 times 3. I have 2 times 3, which is 6, times a -2, which is -12. That means that this has to be a +10 to add up to the +2, and then the -12 to give me 0. But the deal is I have 2 times 1 nitrogen, so I split that +5 up, that +10 up, and that gives me +5 oxidation state for the nitrogen. Now I could have done it right here, knowing that this is a -1 anion, and this is just an easier way to get to nitrogen by pulling the nitrate out. Oxygen gets its charge, -2. 3 times a -2 is -6. My pluses have to add up to -1, so that again is +5. All right, a little bit of practice and you'll have it. And all the answers for almost everything we did is right there. Okay, just a few more slides and we'll be done with this section, and one more video and we'll be done with the chapter. So here we go. In the following reaction, what reactant is being oxidized and what reactant is the oxidizing agent? Well, the first thing we want to do is balance this reaction. So I've got 1 iron, that's not going to hold up. My chlorides are the key to balancing this. I need to get 3 chlorides and 2 chlorides to balance. So I'm going to change this coefficient to 3 and this coefficient to 2 just to get my chlorides to equal 6 on both sides. So that tells me I need 3 magnesiums and I need 2 irons. Now I'm all balanced up. All right, so here's the way we analyze this. And by the way, you didn't have to balance this reaction to to answer it, but we're going to go ahead and do some other stuff with it as well. All right, so here we go. Let's do the easy ones. Magnesium is an element by itself, iron's an element by itself. Those have 0 oxidation states. I've got a chloride ion, that's a -1. It's more electronegative than iron. 3 times a -1 is -3. So that's got to be a +3 because they have to add up to 0. So that's a +3. And I'm not going to worry about that. This one should be really easy because magnesium is an alkaline earth metal, but let's pretend that it wasn't. How would you tell that it's a +2? Because the chloride is more electronegative, and I got 2 of them. 2 times a -1 is -2. So this has to be a +2. Okay, let's go ahead and analyze this. We're looking for what gets oxidized and what is the oxidizing agent. We go from magnesium, which has a 0 oxidation state, to a 2+ oxidation state, that is the element that's getting oxidized, and that actually makes it the reducing agent. Iron 3 plus is going from a 3 plus to 0. It's being reduced, which makes it the oxidizing agent. Okay, and so we can go ahead and figure that out. We're looking for what's being oxidized. That's magnesium. What is the oxidizing agent? That is the iron 3 plus. You might have seen that written as FeCl3. That's totally legit, but this is better. Based on the activity series, which of the following elements is least easily oxidized? All you have to do is go to the bottom. Gold is the least easily oxidized. That's one of the things that makes it so great for jewelry, is it just lasts a long, long time. It's really hard to oxidize gold. So A would be the answer here. Okay, one more. What is the oxidation number of nitrogen in nickel 2 nitrate? NiNO3, and so we actually did this. We did it 2 different ways. We'll do it real quick. You split these things up. What you have to remember is that nitrate is a -1 anion. Okay, so we could simply, oxygen is the more electronegative, 3 times. A -2 is -6. Just remember, this has to add up to the -1 on the nitrate, so that's got to be +5. And so the other way to do it is you figure out that you've got 2 of these -1s. That makes that a +2. So nickel's a +2. Oxygen is the most electronegative. It gets its charge, which is -2. 3 times the -2 is -6, but you've got 2 nitrates. So 2 times 3 is 6, times the -2 is -12. That gives you a +10 here, but there are 2 times 1 nitrogen, so you have to split that +10 up between the 2 nitrogens, and again, +5. Okay.